It's in Catalan, and this is my presentation. The purpose of this experiment is to observe the motion of an object that has dropped from rest and falls somewhat slowly straight down. Somewhat slowly just refers to slower than a rock, so that means that the mass of the mass of the object chosen will be smaller than a rock. This will also be comparing data that has been extracted experimentally, predicted computationally with no drag, and predicted computationally with drag. The experimental side is coming from Tracker, and both the computational sides are coming from Glowstrip. So this will view the effect of gravity alone and gravity with drag on an object. Just as a brief preview, the computational prediction with no drag does not follow the experimental data, and the computational prediction with drag follows the experimental data closer by comparison. Here are the physical principles. Newton's second law relates the net interaction between the system and the surroundings to the observed motion of the system, which is a change in momentum, and momentum is just how easy or difficult it is to change the motion of an object. Drag force in fluid dynamics is the force that opposes the relative motion of an object in respect to its surrounding. So because in this experiment our object will be moving downward since it's falling, this means that the drag force will be opposing its motion, so it'll be pointing upward in the opposite direction. The weight force, or what's more commonly referred to as the force of gravity, is the force that points vertically down on an object. Here, Newton's second law is more commonly seen as F equals ma, but with the momentum equation, it can be found as in another form. The momentum update formula can be found from Newton's second law. It won't be used in the experiment, but velocity update formula will, and it is just a momentum update formula divided by mass, and it'll be used for computational prediction, and the position update formula will also be used, and it's used for computational prediction. The weight force is the same as the force of gravity. In this case, it'll be equal to negative mg j hat. M is mass, g is the acceleration due to gravity, and j hat is the direction of the standard unit vector for the y-axis, which is given as 0, 1, 0. The drag force is given as minus b times the magnitude of velocity squared times j hat. B is the proportionality constant. Because our object will be falling downward, this will be from the force of gravity, or the weight force. It'll be moving in the negative direction, meaning downward. So as a result, the drag force will be pointing upward, which is opposite in motion. So in reality, we will not be using this negative sign. It is more so just telling us or representing that it'll be in the opposite direction of the motion. Here is our object in motion. So the system is an orange dryer ball. The surrounding is everything but this dryer ball, so the floor, the air, and the earth. The initial position is usually 0, 0, 0, but Tracker gave us 0, negative 3.396 e to the negative 3, and 0, so this is what we use, and the initial velocity will be 0 meters per second because the object is starting at rest. So here we have the mass of the dryer ball, which is 3 grams. Here are the initial conditions. The video is shot at 30 frames per second, which gives us delta t. Here is g, j hat, and the proportionality constant is set to 0 because we are assuming that there will be no drag force in a gravity-only scenario. The total video is 0.367 seconds, so this is the final time. Here, drag force would be calculated, but we are just simplifying it as a 0 vector. Here, weight force is calculated. Net force is calculated by adding these two forces together. Here is the velocity update formula, and here is the position update formula. Here are the two graphs that are given. Note that the position is referring to the y position instead of the x position. Here is gravity and drag alone, so everything is the same. The only thing that changes is the proportionality constant, which actually has a value. This was found by essentially guessing a number and increasing and decreasing until it eventually fit or was closer to the experimental data. And here, everything is the same, except we are actually calculating the drag force as seen here. These are the results, the position versus time graph, and the velocity time graph. So comparison. Here the yellow line represents the computational prediction with drag. The gray line is computational without drag, so just gravity, and the blue is experimental. So as you can see, the only gravity severely deviates from the experimental value, while the computational with gravity and drag fits closer to the actual experimental value. But as you can see, there is deviation near the middle. This could be because there is bad points per frame chosen. Maybe more precise ones could have led to a more accurate representation. There are variable time frames. If a faster time frame was chosen, there would have been more points, so it might have created more points for it to be more accurate. But more realistically, a better proportionality constant could have been chosen because this could have leaned the predicted values closer to the experimental. And here are the questions. Which predicted model, if any, predicted terminal velocity? So terminal velocity is a constant speed reached from a falling object once there is no eventual resistance, meaning there's no acceleration. In reality, neither of our models show this. Here is gravity and drag. As you can see, there is no constant velocity. And here is gravity only. There is no constant velocity, which would be a flat line. And here it's the same thing, but instead we are throwing the object initially instead of making it fall at rest. So the question is the terminal velocity the same in this case? So terminal velocity would be the same because regardless it's the constant speed that it's eventually reached. It would just be reached earlier because there is an initial position now, or sorry, initial velocity. So if this were to eventually plateau and reach a constant velocity, as you can see, whether it started at 0 or whether it was lowered down to initial position,